This project demonstrates the design and performance of the thermal in situ sustainable remediation technology, known as TISR. The demonstration project was selected in 2020 and operated between 2022 and 2024 at a site undergoing remediation at the Vandenberg Space Force Base in Lompoc, California. This is Project ER20-5028 of the Department of Defense Environmental Security Technology Certification Program, or ESTCP. The work was designed and implemented by Arcadis in collaboration with experts from Clemson University and California State University Long Beach. In this illustration of the TISR technology, you can see the subsurface heating system powered by solar radiation and waste heat sources delivered via a closed-loop heat exchange system. TISR is a heat enhancement technology designed to elevate subsurface temperatures in a controlled manner to expedite treatment processes. Utilizing solar radiation and waste heat sources, TISR systems heat the subsurface through a closed-loop heat exchange recirculation system. By minimizing energy consumption and reducing greenhouse gas emissions, TISR provides a sustainable solution, enabling faster cleanup and cost-effective remediation. The primary performance objective of the study was to accelerate the treatment rate by enhancing degradation rates through modest increases in temperature with solar collectors. Additional objectives focused on demonstrating the efficiency of subsurface heating through the TISR technology and using the abundance of data collected during the project to confirm treatment mechanisms and support detailed modeling. The ultimate outcome in mind is to validate design and technical performance criteria for the technology so that guidance can be used for wider applications. With those objectives in mind, and based on the site selection screening criteria shown here, Site 15 at Vandenberg Space Force Base was chosen for the demonstration project. Site 15 fit the objectives due to its low permeability, persistent source mass, and complex heterogeneous geology. Now, we will briefly describe the system components before getting into the details of system performance. The TISR system at Site 15 focuses on the area around monitoring well MW41, circled in orange on the map to the right. MW41 has seen persistent CVOC parent and daughter products. Below grade, the system features 8 borehole heat exchangers, or BHEs, with a heating interval from 20 to 40 feet below ground surface. The system also includes 8 new performance monitoring wells with shallow intervals from 17.5 to 27.5 feet below ground surface and deep intervals from 30 to 40 feet below ground surface. 2 existing monitoring wells, MW41, with a screen interval of 19 to 39 feet below ground surface, and MW8, with a screen interval of 25 to 35 feet below ground surface. 2 new soil vapor probes, with a total depth of 17.5 feet below ground surface. And 12 distributed temperature sensing fiber locations, or DTS locations, covering intervals from the surface to 40 feet below ground surface. Above grade, the setup includes 8 solar collectors arranged in a 4x4 array, along with 1 conveyance piping manifold and 1 pump station with telemetry and system safety interlock features. TISR systems are fully remote in their operations and monitoring. Shown here is a system dashboard that allows the operator to track and manage several key parameters during remediation. This tool allows for constant system adjustments and reduces the number of site visits needed, ultimately resulting in cost savings and a reduction in the carbon footprint over time. This also allows for a high density of data logging, enabling analytical assessment of system performance. Next, we will describe the performance objectives of the technology and share results from the demonstration project. EVS software is utilized to evaluate DTS temperature data. Its 3D kriging and viewing options for geologic and temperature data provide a detailed and immersive visualization experience. The time series animations enable the observation of temperature changes over time, helping to identify trends and patterns. For ease of sharing and collaboration, output data can be exported to an interactive 3D web scene viewer. Based on the transect shown on the site map to the right, this graph shows groundwater temperature increases at MW41 during TISR operations. The TISR field demonstration around the MW41 area began in May 2022. Shown in the 3 vertical profiles to the left, groundwater temperatures collected from the DTS fiber recorded BHE operational temperatures between 40 degrees Celsius and 50 degrees Celsius. The high-resolution temperature data provides a detailed vertical and horizontal profile of temperature distribution through the targeted heating zone. This temporal data shows radial heat distribution away from the BHEs, along with an observed vertical temperature rise moving down gradient. Point source temperature monitoring within MW41 reached temperatures of approximately 25 degrees Celsius at the end of 2023. It should be noted that MW41 is located within the coldest area in the heated zone, approximately 10 feet from the BHEs, marking the centroid of the BHE grid pattern. The team developed a prediction model to help evaluate solar insolation and heat distribution in the subsurface based on site location and geology. We then used the model to determine the appropriate spacing for borehole heat exchangers and identify the required heating source infrastructure. That, in turn, helped us estimate the time required to reach target temperatures using the predictive model. The sequence of temperature modeling shown here shows how the subsurface borehole heat exchangers were expected to increase temperatures over time. The image in the upper left is expected BHE performance at 90 days, and next to it is the modeled increase at 180 days. Below that, you can see the temperature increases surrounding MW41 after 365 days and 730 days. We now compare the model predictions to field data. You can see here, in an example from DTS fiber data at location DTS7, that the data appear to track the model very well until 2023. At that time, there was a significant rainfall event, and we can see the influence of surface water in the data trend lines represented by the series of dots below the model's dashed lines. Even after that event, this chart shows that the actual data tracked the predicted temperature trends very well, and we saw a comparatively good estimate. Monitoring Well 41 is a legacy well at the site and serves as a remedial compliance well. This graph shows long-term trends of CVOCs over time. You can see the several bioremediation injections over time, followed each time by a rebound of CVOC concentrations in groundwater. These data indicated the need for enhanced treatment via heating. After TISR system startup in May 2022, you can see the CVOC concentrations significantly decreased and remained low through the year. Over the demonstration period, TCE dropped from 550 to 7 micrograms per liter, DCE dropped from 3,500 to 200 micrograms per liter, and vinyl chloride dropped from 830 to 110 micrograms per liter. Confirmed in another way in this time series chart of data from MW41, we can see the changes in molar fraction over time as parent products are effectively degraded to non-toxic daughter products during heating. This shows desorption of the parent TCE compound as temperatures increase, with subsequent reductive dechlorination proceeding through detoxification. The change in chlorine number to less than 1 suggests complete transformation from chlorinated parent molecules to non-chlorinated, non-toxic end products. Supporting the performance seen at the compliance well MW41 is data from newly installed wells nearby. As shown here, data from a new well displayed a significant amount of the parent product TCE located within the shallow water-bearing zone when this well was installed. After TISR startup, the concentrations of TCE briefly increased, followed by rapid and sustained decreases in all CVOC concentrations in this well. Note that this heat-induced degradation was achieved without the need for further amendment injections. Similar to what was shown for molar fraction change over time at MW41, the change in molar fraction over time in the newly installed well showed parent products degrading to non-toxic daughter products. You can see the significant shift in molar mass from TCE and DCE to ethene and ethane, and the corresponding decrease in chlorine number. This infographic shows the shift in bacterial populations during the project from baseline to 8 months later. Using Microbial Insights QuantArray data, the black bars in the graph show increases in bacterial populations. For example, microbial data from October 2021 and January 2023 show a significant rise in D. Helicocoides populations and other key bacteria. These shifts in populations correlate with the temperature increases observed during the TISR enhanced in situ bioremediation. Shown another way, we can see in these comparative charts how populations of bacteria have shifted due to the enhanced heating during the project. Next-generation sequencing data show shifts in diversity and abundance of bacterial groups as temperatures increase from roughly 18 degrees Celsius to roughly 24 degrees Celsius. For example, as temperatures increased, there was a shift in the dominant bacteria present in the subsurface. We now turn our attention to summarizing the key outcomes and advantages of applying the TISR technology relative to alternative approaches. The key outcomes of this demonstration project include an average temperature increase of approximately 6 degrees Celsius, with a maximum temperature increase of roughly 15 degrees Celsius near the BHEs during 18 months of operations. Observed an increase in the abundance of key bacteria associated with reductive dechorination, correlating with rising temperature. Accelerated biodegradation rate, evidenced by comparing decreased concentrations of VOCs and chlorine number over time. And potential reduction of the active remediation timeframe that could result in reduced lifecycle costs and a minimized carbon footprint. Some of the key advantages of the TISR technology include complements traditional remedial methods by rate acceleration and enhanced mass desorption. Particularly effective for treating contaminants in low permeability soils. Utilizes renewable energy sources and remote monitoring for self-sustaining operations. Incorporates reusable and modular components to optimize costs and sustainability. Reduces remedial timeframes and life cycle costs. In conclusion, we would like to share our appreciation to the project team who had a part in this demonstration. Principal investigators were Dr. Craig Devine of Arcadis and Dr. Ron Falta of Clemson University. They were supported by several experts from Arcadis, Clemson, and California State University, Long Beach. The team also acknowledges and appreciates the support from ESTCP and Vandenberg Space Force Base for their support of this work.